All right, so there are several methods of measuring soil water potential, especially out in the field. In this video, I'm going to show you a couple of the devices that are commonly used for detecting and measuring soil water potential in a variety of environments. So the first device here is called a tensiometer. Tensiometer is just what it looks like here. It's a plastic tube, but down at the bottom you'll see a ceramic tip. This ceramic tip is going to be really useful for having water move in and out of the device. I'm just going to show you the parts first, and we'll talk about what they do in a moment. At the top of the tube, you have a pressure gauge, and then you have this little, what it is basically a pump, because you're going to be working with pressures here. So if you were to work this, you would just put water inside of here, take the cap off. I'm doing this one-handed. And then once you get it, you can start pumping it like this. That's too far. There you go. And that'll start to increase the pressure. So a tensiometer is used out in the field quite commonly. It's an easy-to-use device that is something you can install in many locations. The problem is it's hard to computerize, it's hard to maintain because you have to constantly keep the pressure up in it. So a tensiometer like this, what you're going to do is you're going to pour water into the top. Up here, you're going to pour water into this cup and start to fill up the tube. You fill up the tube to the very top, and you've got to maintain that. Why you have to put water in it is because down here at the bottom, that ceramic tip here, this is actually semi-permeable. It is. It looks solid. It looks like it's made out of ceramics like bowls or plates, but this ceramic tip is actually specially designed so that water can move in and out of this tube. So you've got little micro pores in here. You can't see them even if I get close up like this, but they are small enough that water can move across given enough force or pressure. So what you do with a tensiometer is you fill it up with water. And when you do that, that water is going to be pooled down here at the bottom. Then you take the tensiometer and you're going to bury it into the ground up to where the pressure gauge is. You're going to take the top here and press it a bunch of times like I showed you. That's going to bring up the pressure in the gauge, as we can see here. So you bring up the pressure in the gauge, bury it, and then you let it sit. And what happens is the water inside the tube and the ceramic tip are going to try to equalize pressures with the environment, the soils outside of the tip. So if you put this in, the environment inside the tube is going to be completely saturated. It's going to be wet. Well, if you put it into a soil that is also wet, completely saturated, then there's not going to be any exchange because both of them are going to be completely saturated. There's no need to equalize pressure because they're already at the same pressures. However, if you put this tube and the tip that are completely saturated with water into the ground that is maybe half saturated, it's moist, but not completely saturated. Well, what happens then is that the soil, the matrix potential from the soil particles that are surrounding the tip are going to be pulling the water. They're going to be sucking the water out of the tip of the tube here. And so you're going to have water that is moving from your tube and the ceramic tip going to be moving out into the soils. Well, when that happens, you've got the top that's sealed here. If you have water that's being sucked out of here, that's going to create a pull, a pull down here, some pressure. That pressure is going to be detected in this. And so if you're at complete wetness, if it's completely saturated, the dial's not going to move because you don't have any suction. However, if you have a soil that's drier than what's in your tube, which is completely saturated, then it's going to suck the water out of it, even just a little bit, and that suction is going to create pressure inside the tube. It's going to create pressure inside the tube, and that's going to be detectable in the pressure gauge. This is no different than a pressure gauge for a tire or anything like that. It's just looking at things a little bit differently. And so as the pressure inside the tube increases, the dial on this is going to slowly go up, which means that the drier the soil outside of your tube, the higher you're going to see this gauge go, because there's going to be more suction of the water out of the tube, because more water is traveling or being sucked into the soils outside of it. And so you can see, even on this gauge, 100 here means that it's dry. And you can see here, it's a little fuzzy, but it says this is measuring things in centibars. Bars are a measure of pressure. And so depending on how much suction you have, that's going to control how many bars of pressure are induced inside the tube here. So it's all looking at exchange of pressures. Pressure exchange within the tube compared to the outside of the tube based on what's happening with this semi-permeable porous tip. So that's the first device. The second one here is called a G-block, a gypsum block. And the gypsum is just happening in this little device right here. This is a gypsum block. Nothing special about it. But we can take advantage of some of the properties of the gypsum. Gypsum has a very high affinity for water, which means that it likes to absorb water. Kind of unusual. You don't usually think of a rock absorbing water because gypsum is a rock, but it acts somewhat like a sponge in that you put this into a soil. So you would just bury this into a soil, and if the soil is wet, the gypsum block will absorb some of that water. If the soils are dry, any water that was in the gypsum is going to be released out into the soils. And so we can actually take advantage of that by detecting how much water is or is not within this gypsum block. And we do that by sending a small electrical signal through the gypsum. We do that because the more water that is inside the gypsum, the less resistance there is to a small electrical pulse. Now, this isn't enough to shock you. You wouldn't even notice it. It's very, very minuscule. But if there is water inside the gypsum, the resistance for electricity to move through it is going to be less. If you have a completely dry piece of gypsum, the resistance is going to be pretty high because that electricity has to move through air. Electricity does not like to move through air. It would much rather move through water. So we can take advantage of that by sending a small pulse of electricity through it, and depending on the amount of water available in that gypsum, or amount of water that is stored in that gypsum, is going to affect the resistance. More water in the gypsum means less resistance and a faster pulse of electricity. We can detect that by using a monitoring device like this. So you have your gypsum block that's connected to electrical cords like this. At the end, you have some transistors. What you're going to do is actually just plug these little metal pieces that are connected to the wire onto the nodes, the little metal nodes that we have here. I'm not going to be able to do it very easily with one hand, but you get the idea. You have one here and one here. Okay, there, I got it. So once you get those connected, you'll see that there's a readout here. And all we have to do is press the read blocks button to be able to see if there's anything there. Now, I don't have the gypsum in anything, so I don't actually know if we're going to get a readout. Let's see. Yeah, 0. Because there's full resistance, and we're not getting anything out of that. If it was completely water, it'd be something more as a higher number. But what this is doing, what this detector is doing is looking at resistance. So it's not actually looking at the water potential itself. So the number that we get out of here is just electrical resistance. We have to then take that number and use a calibration curve that looks like this to be able to determine what the soil suction or the soil water potential is based on that resistance. So you can see here on the axis, soil moisture meter readings, right there. So that's coming from this. You find your number, say we had 50. I'm just making up a number here. You had a reading of 50. You'll follow that across to this calibration curve. This curve goes all the way across. So you follow that down, say we said 50, you find where it hits your line, and then you just follow that down. So it came down to about 45, I would say, 0.45. That's how much suction you have in bars. So remember the tensiometer was in centibars. If I can get that right side up. It was in centibars. I can't focus it very easily, but it says centibars there. Centa means 100, so it's 1/100th of a bar is what that was reading. This is reading it in just plain bars. So we had 0.45 bars of potential or pressure. So that's how you use this. You're looking at electrical resistance in a block of gypsum. You read the resistance here. You equate that resistance to pressure or pressure potential here, or suction. We can call it either one. The last method that we can use is using TDR, so time domain reflectivity. It's using the same basic principles as the gypsum, looking at electrical impulses, but you're only using a probe. You're just putting a probe into the ground, and it's reading resistance from that. And then it'll read something out on this. I don't have it in the ground, so it's not going to work, but that just gives you an idea. You can just stick a probe into the ground and it'll give you a reading. Pretty simple. And you can connect that to a constantly monitoring computer device so you can get minute-to-minute changes in soil water. Especially useful for places that are really concerned about their soil water content, such as dry regions that are focused a lot on irrigation and figuring out, do I need to irrigate or not? Something like that is really useful to connect to a computer so the computer can start figuring out, hey, are we getting low enough numbers to activate the irrigation system? So those are the 3 different methods that we can do. The one that we are going to be focused on today with our lab is detecting soil water potential using the gypsum block.